Let's now investigate how the van der Waals model actually predicts a phase transition. We know that it predicts a region of instability. Wherever the pressure versus volume isotherm has a positive slope, the system will be unstable and unable to exist there. Let's draw the outline of the unstable region for a variety of isotherms. Here I've drawn the critical isotherm in green. Hot isotherms with a temperature above the critical temperature in these three above, T greater than 1, and some colder isotherms below. What I'll do in this blue marker is mark out the points of mechanical instability. In between these two blue dots, the system will be mechanically unstable. And even though I've only drawn a few isotherms, we can imagine that each isotherm in between the ones that are depicted has its own point where instability begins. So on the left, we've got that, and on the right, we'll have something like this. And there's a critical point where these two sides come together as the region for instability actually disappears at this critical isotherm. So in between here, this entire region is a region of instability on the PV diagram. The system cannot exist there in a pure state. So this is instability. Right at the top of this region, at the peak, we have our critical point. So we've been able to predict from the van der Waals equation of state where the critical point is. Here in terms of reduced variables, it's just at 1, 1. And we've been able to realize that there is a region of instability. But we still don't know exactly how a phase transition can happen in this system. And to do that, we're going to need to take a look at the free energies. First, let's look at the Gibbs free energy. I'm going to erase this diagram, as nice as it is, and draw an isotherm which is clearly in the unstable region. On the top, let's draw a graph of pressure versus volume for a temperature that is less than the critical temperature. And on the bottom, let's draw a second graph. This graph will depict the Gibbs free energy, G over N, as a function of pressure. Remember, pressure and temperature are the natural variables for the Gibbs free energy, so we have to draw them in terms of pressure. I've got two axes set up here, and what I want to draw first is how the Gibbs free energy would behave for a van der Waals gas. So on the bottom graph, let's depict the reduced Gibbs free energy, which will be G over N. Now remember that the Gibbs free energy is a function of temperature and a function of pressure. So in order to draw any real conclusions from this, I need to plot the Gibbs free energy versus pressure. To have the graphs match up, I'll also plot the van der Waals isotherm in terms of pressure versus volume. But let's just get our bearings here when a graph is volume versus pressure. We'll let the critical point be here, and I want to draw an isotherm that is below the critical point. So that will have an asymptote at V equals 1/3. It will come past the critical point, have an inflection, and then have a vertical asymptote at 0 pressure. So this will be the general shape of my isotherm for a temperature that's less than the critical temperature, or a reduced temperature of less than 1. Let's label several points on this curve. First, I'm going to label 3 important points. These important points will all have the same pressure, and I'm going to label them as C, E, and G. Where do these points get located? Well, they must be somewhere in the region where there are 3 volumes for a given pressure. But furthermore, I'm going to stipulate that the Gibbs free energy at location G and the Gibbs free energy at location C are equal. This is possible, as we'll see in a bit, but it will help us to define where these points are actually located. We'll then say that this is location F, this is location D. At an equal pressure to F, I'll put another dot and call it B, and way out here at some high pressure, location A. Going the other direction, at the same pressure as location D, we'll put a location H. So let's be careful here. P at G is equal to P at E and P at C. Those are all the same pressure. Vertical line there. The pressure at B is intended to be equal to the pressure at F. F is right at this maximum pressure point. And the pressure at C is equal to the pressure at H. C is the pressure, sorry, not C, D. D is the pressure at this minimum point here. And then one more point to label, as if there weren't enough, we'll put a pressure, a location I out here at high volume. Now, how can we construct the Gibbs free energy graph from this isotherm? Well, let's remember one of the defining relationships. dg dp is equal to the volume. So the slope of this curve here, or not the slope, but the volume value on this curve will be corresponding to the slope of that same location down here. That's not so helpful to draw the graph, but a slightly different version of it is. Delta G is equal to the integral of v dp. So I've got P as my horizontal axis. So areas that are enclosed on this curve will be corresponding to changes in the Gibbs free energy on this curve. Now, one thing to realize about these integrals is if we go from left to right, then we enclose a positive area and a positive delta G. If our curve takes us from right to left, as it does from F to D, then we have enclosed a negative area, and we'll see a decrease in G. So what we're going to see roughly as we go from I all the way to A is we're going to see an increasing Gibbs energy, then a decreasing, and then an increasing Gibbs energy. So the graph here is actually not going to be single valued. Let's start at I, which will be the lowest Gibbs free energy on the plot. As we go from I to H, we're at the same pressure all along a vertical line here. So as we go from I to H, we have a change in Gibbs free energy due to this area here enclosed between these two vertical lines, the axis and the isotherm. So we have a positive increase in the Gibbs energy, which is rather significant compared to the rest of the graph. From H to G, we get an area between these two lines, all the way from the axis to the isotherm. So we get another increase up to location G. Then from G to F, so G, G is meant to be on a line with all these here. So this is This is the pressure of I, this is the pressure of H, and this is the pressure of G. So G will be a slight increase from there. That would be location G. On to location F, we get yet another increase. But that's our last increase for a while in terms of the Gibbs free energy. Because as we go from F to E, we get a decrease in the Gibbs free energy, and we go back to pressure at the pressure of same pressure as G. So we get a decrease here, but the decrease from F to E is not as large as the increase was from G to F. See, G to F is the area from here to here, and from the bottom to the isotherm up there. From F to G, the area is from this lower curve. So in going from F to G, we actually decrease less. From going from G to F, we increase more than we decrease from going to F to E. So E is up here in Gibbs free energy a little bit above location G. All right, then let's go from E to D. D has the same pressure as H, and it's another decrease. And let's think about how big this is. From H to F, we have this entire area here. Then from F to D, we have this area here, so that's less. So D is still above location H somewhat. And since from D to C we're going to increase Gibbs energy, D is below location G as well. Okay, then we go back from D to C, we get another increase, and by definition of locations of G and C, they have the same Gibbs free energy. So G and C are at the same location on this plot here. Then from C to B we get a small increase, and from A over to A we get kind of a bigger increase, but A is way out here. Okay, so wasn't that fun? Now let's connect the dots from I to A, following in the same order as they were on the isotherm for the V versus P. So let's go. I to H. We know the order of the alphabet, right? I, H, G, F, E, D, C, B, and then I guess I don't want to make it look like there's a kink in there, so B to A, so like that. So we get this weird kind of loop-de-loop in the Gibbs free energy versus pressure curve. And what the heck does that mean? Well, the slope of this curve at any point is the volume, right? So down here, we're at high volume, between around H and I, high volume. Over here, between F and A, we're low volume. And the volume should always be, right, at a positive value. So the slope is always positive. So that's good. But in addition, this curve should always have, the correct concavity. This curve G versus P was supposed to be concave down. So from F to D, we've actually got this region of instability. So these solutions up here that I'll mark in red from between F and D, these are the states in the middle here of the isobar, the isotherm from F to D. Those were mechanically unstable. Mechanically unstable. But what about the rest? As we take the system from I to H to G to F, there becomes multiple options, right? At a pressure equal to the pressure between, if we are at a pressure between C and B, we could either be on this lower curve, or we could be on this second curve in the middle. We can't be on the top one because that's unstable. But we could be on either of these. But which one does nature choose? How do we know? We return to the principle from the second law of thermodynamics, that the ultimate global equilibrium state at a certain pressure value, at a certain temperature, isotherm, will minimize the Gibbs free energy. So the state which is realized in nature, the most stable global equilibrium state, is the one that has the lowest value on its Gibbs free energy curve. That means that the real system, if it's taken from I to H to G, will follow this pattern. It will not go on this piece between D and H, because that has a higher Gibbs free energy. As it continues, it will jump straight to point C and continue this way. It will not go from G to F, because that has a higher Gibbs free energy. So what we see now on this plot is a system. Imagine we begin at I and begin decreasing the volume of the system, compressing it. So we have a high volume here, a high slope. We keep having a high slope. We keep having a high slope. We've entered this region where some instability is possible. We don't even know it yet. We're going from H to G. Then suddenly we get to this point at G, and something special happens here. We have to change our slope from one value to another. Remember, slope is volume here. So we have a discontinuous change in volume between the slope just before G and the slope just after C. That discontinuous change in volume is the phase transition. We skip this whole region here. We go straight from G to C. And then we continue on with our compression. So that is how we see the Gibbs free energy informing us about how a phase transition happens in this van der Waals model. What we look for is a region where the Gibbs free energy has multiple values or multiple possibilities, and the maximum entropy will be when the Gibbs free energy is at its lowest. So the lowest value of all the possibilities is the physically realized state. Now this brings up some interesting questions about what goes on between F and G. So between F and G, the system is mechanically stable, and if it was started, say, somewhere between F and G, it would be able to stay there for a while. It wouldn't necessarily immediately know that there was a lower state of Gibbs free energy possible. So between F and G, there's no problem having the system there, right? The curve has the right slope and the right concavity. So these are called states that are metastable. And there's another one between D and C. Between D and C, so down there. So these states that I've marked in blue are known as metastable. They're fine to exist, but they're not the minimum possible Gibbs free energy. They're not the maximum. And it might take some time for the system to figure out that these states are not the most stable. If I can try to draw on your experience here, maybe you've heard of situations where people have water bottles. They're camping or something, and it's cold overnight, and they have their water bottle, and it looks like it's fine. It's just liquid, but as soon as they grab it, it turns to slush. It suddenly freezes. And it's said that their water was in a super cooled state. It had no perturbations, no dust in it, nothing enough to get it to actually start to freeze. But it somehow found itself at a temperature below zero. So that would be putting the system into this metastable state. Any sort of disturbance might knock it over onto this mixture region. Basically, this is the mixture region here, the green straight bar. But it can exist there. So there's situations of super cooled water suddenly freezing. You might have also heard that if you take water out of a microwave after heating it for a while, sometimes you have to be aware that if you suddenly throw a bunch of salt in there, it might suddenly decide to boil it might actually have been superheated where it followed just so gingerly along this metastable curve over, over to this point somewhere in here, but never got that one little kick it needed to begin the phase transition. So it gets superheated, and then throwing a salt crystal in there, which is rough, will certainly set it off, and suddenly it will turn into a mixture of water and steam, and probably splash all over the place. It's quite dangerous. So these kind of phase transitions are well described by the Gibbs. We get a really rich description here, right? We get a discontinuous change in volume. We get a description of these metastable regions, the unstable region, and this whole isotherm here too. So how might we go about finding where this phase transition actually happens? Well, we just have to go back to our assumption that somehow we could find a location, two locations actually, G and C, that had equal Gibbs free energies and equal pressures. So if we want to find or predict the phase transition in the van der Waals model, we have to first choose a temperature. We choose a temperature. The phase transition here is interpreted as one that happens while we compress or expand. So we choose a temperature that gives us an isotherm. To find or predict a phase transition, we need to look for a phase transition pressure. This pressure is historically called the vapor pressure, because when you have a mixture, this is the pressure that its vapor has when it's in equilibrium with itself. That would be along this vertical line here. It's at one pressure. So you find a vapor pressure PV right there, right here. Find a vapor pressure PV where the Gibbs energy has three values. Three possible values, and two of them are equal. So at most points within this region, if we pick a pressure between pressure of C and pressure of F and draw a vertical line for that pressure, we'll get three possible volumes, right? Three possible volumes and three possible Gibbs free energies. Say there, there, and there, or there, there, and there. So three possible Gibbs free energies for every pressure. But at one specific point, there will be three Gibbs free energies, one that's high and two that are low and equal. And that is the point where these two curves cross, and that is the point where the phase transition occurs. But what we can do is use volume as a parameter to plot curves like this, and to plot the Gibbs energy curve like this. And then we can use a graphical approach to try to look if there's a crossing or this loop kind of behavior on our Gibbs free energy plot. G versus pressure, a parametric plot parameterized by volume, and then try to zoom in on this crossing point just by making successive graphs to try to get closer and closer to it. We can gain more insight into the phase transition by looking at an alternative method in terms of the Helmholtz free energy. I've drawn a plot of an isotherm with a temperature less than the critical temperature, labeled the points in the same way as I did for the Gibbs plot. Down here I have the Helmholtz free energy versus volume. The plots are now versus volume because volume is the natural variable for Helmholtz. The derivative relationship between Helmholtz and volume is going to be an easy relationship of the pressure curve. The slope of this curve down here will be the opposite of the pressure value. So when we have a high pressure, we have a steep slope. And when we have a low pressure, we have a flat negative slope. When the pressure is positive and decreasing, we will see down here a function that has a negative slope and a positive concavity. When the pressure is increasing, we will see a negative concavity. So what we expect to see for this Helmholtz energy curve is one that is negative with concavity up, then it has an inflection to concavity down, and then it still slopes down negative with concavity that's up. So let's draw these points here, realizing that we're going to start at A, which is a high value because it all slopes down from there. So we'll start with location A here and go to location B. B is just between A and C, and we've got a pretty large pressure here, so we're going to see a pretty large negative slope. So down to location C, we will get a pretty significant drop. So we'll go like this, there. And then on to location D, we've got a smaller drop, but now what happens at location D is we have an inflection point. So we still have a negative slope, but we now have a change of concavity. Between D and F, we have a situation where it is concave down. So between D and F, we have a slightly concave down. And then after F, we go back to a decreasing pressure, so a upwards concavity for this free energy function. Still, it's a positive pressure, so still we have a decreasing function. But now we're going to have something like this all the way out. All right, so there's location G, H, and I is way down there. The Helmholtz free energy can become negative, so this doesn't have an asymptote. It actually behaves logarithmically out at high volumes. But that's sort of what this looks like. Now, how the heck can we look at this and tell whether there's a phase transition or not? So for Helmholtz energy, we pick a temperature, and we pick a specific volume, and we look for where the Helmholtz free energy is minimized. But look at the graph. There's only one value. A specific volume seems to give us a specific value for this Helmholtz free energy. So how can we get a phase transition here? The key is going to come first by realizing that there is this unstable region here from D to E to F. The pressure increases with volume. The free energy curve has the wrong concavity. And so we have a region that is mechanically unstable. In our discussions of the Gibbs free energy, we realized that since C and G had equal Gibbs energy, that the phase transition would happen on a pressure isobar directly from C to G, skipping all these metastable and unstable states. But what happens on the Helmholtz diagram? Well, let's think as if we're a gas. And we've been placed somewhere with a volume between C and G. Now, we could choose to adopt a volume, like say we've been placed between F and J. We could choose to adopt a volume right here, right? That's on the curve. That's allowed. But we actually could get a decrease in our energy by doing something clever. What's the clever thing that we can do? Well, rather than sit at this value here, which might be rather high, this system could form a mixture. Between two other points on this curve. Any 2 points on this curve could serve as two systems which are mixed together. And the Helmholtz free energy of any such mixture would simply be a straight line between those 2 points. But is that going to minimize my free energy for me? Well, I wouldn't be able to minimize it by going out to the far extremes from this, because then I would have a negative percentage of one of the mixture components. So I'm stuck between them. And so if I'm at a point, like if I'm sitting at a Helmholtz free energy at location F, turns out that I could achieve a lower Helmholtz energy by, instead of being a homogeneous substance at location F, by splitting up into a mixture of 2 pieces with a Helmholtz free energy of one at location G and the other at location C. That would lower my Helmholtz energy to this straight line. So our conclusion here is, on the Helmholtz free energy graph, regions of instability can be covered by lines that are called convex hulls. So this line here is a convex hull, where the system has a concavity, where there's a place where it's concave. We can imagine bumping up a straight stick or a ruler to that, bumping up a straight line and pushing it as tight as it can go. The line won't be able to go into the concavity, but it will provide sort of a bridge from one place on the convex part of the curve to the other part of the convex curve. So the combination of a convex curve, the line, and the convex curve on the other side is always convex. It doesn't have any concavities anymore. So that's called a convex hull. Anytime we have a region that's concave, we can always place this convex hull over it and cover it up. And that convex hull then becomes a line which is lower than the region of concavity, and some stuff on the some stuff next to the region of concavity that is next to it. So our system, if it was taken along a trip, would come down here. At point D, it would think, well, I could stay metastable and have this slightly higher Helmholtz energy. That might be okay for a while. Eventually, I would get unstable, though. But what I could do also is I could just start forming some gas, right? At location D, we're at low volume, we're gas, we're liquid. At location G, we're high volume, we're gas. So I could just start forming some gas and letting that give me some Helmholtz energy that's lower. And then I'll just slowly form more gas and increase this mixture until I'm all gas at location G. And then I can't really form I can't eliminate any more liquid to lower my Helmholtz free energy, so I'll just have to go along the gas curve like that. So that's the phase transition in terms of Helmholtz free energy. We come down to a point C. We slip onto this line, which has a constant slope, a constant negative slope, which means a constant pressure. So we go over then until we get to location G, where the slope of the actual Helmholtz energy curve matches the slope of the line, and then we continue on the actual curve. Right? The regions of metastability here are between the regions of instability and the regions where this convex hull line touches the free energy curve. So between here and here, between C and D, and between F and G are the regions of metastable states. Okay.